We often treat Mars as our inevitable second home, a cosmic backup plan waiting for our arrival. But the reality of the red planet is far more hostile than we like to admit. The barriers to living there are not just engineering puzzles waiting for better technology. They are fundamental limits of biology and physics. From relentless radiation that degrades human DNA to low gravity that slowly weakens our bodies, Mars is a world actively trying to reject us. In this slow-paced documentary, we look past the hype to examine the quiet, terrifying truths of Martian colonization. Designed for calm observation and winding down, this video allows you to explore these massive cosmic challenges at a restful pace. Let your thoughts drift across the cold Martian landscape and out into the silent, vast expanses of the universe beyond. Mars is not a fixer-upper. It is an active existential trap. The surface pressure averages a mere 0.6% of what we enjoy at sea level on Earth. Its thin envelope of air is a suffocating chokehold of 95% carbon dioxide, featuring a vanishingly small fraction of a percent of oxygen. To step onto the Martian surface unprotected is not a test of endurance. It is an immediate physical termination. Within 15 seconds, your brain would starve of oxygen, plunging you into unconsciousness. Within 2 minutes, the systemic structural failures of the human body would become completely irreversible. The terrifying reality of Mars is that it doesn't care about our technology. We have built tools that can look back to the dawn of time, and rovers that can cross alien sands for decades, but none of that changes the baseline physics of the red planet. Mars is not waiting to be conquered by engineering. It is an inherently broken world that cannot hold onto the things life requires to persist. As we unpack the layers of this environment, it becomes clear that our dreams of a backup planet are pulling us toward a destination that doesn't just resist human presence. It actively erases it. Act 2. The anatomy of a thermal freefall. To understand why Mars is an environment of pure, unyielding crisis, you have to look first at the solar arithmetic. Because Mars orbits nearly 50 million miles further from the Sun than Earth, it receives only about 57% of the solar energy that strikes our world. This deficit changes everything. It means the planet is fundamentally starved of raw warmth from the outset. But the true horror of the Martian climate is not simply that it is cold. It is how that cold operates without a governor. On Earth, our thick, dense atmosphere acts as a massive thermal flywheel. When the sun sets, the billions of tons of nitrogen, oxygen, and water vapor blanket the surface, trapping heat and releasing it slowly over the course of the night. This atmospheric insulation ensures that a scorching desert day doesn't immediately plummet into an Arctic nightmare. Mars possesses no such buffer. Its air is so thin, so depleted of mass, that it cannot store energy. The atmosphere isn't a blanket. It is a pane of glass that allows heat to escape into the vacuum almost instantaneously. Consider the absolute best-case scenario Mars can offer. On a peak summer afternoon at the Martian equator, the temperature right at the surface can climb to a remarkably pleasant 70 degrees Fahrenheit, or about 21 degrees Celsius. For a fleeting moment, you could stand there and imagine you were in a park on Earth. But this is a thermodynamic illusion. As soon as that patch of ground turns away from the sun, the temperature collapses into a terrifying abyss. Within 12 hours, that exact same spot will plummet to minus 100 degrees Fahrenheit, negative 73 Celsius. A daily temperature swing of 170 degrees Fahrenheit. There is absolutely no analog for this anywhere on Earth. Our most extreme terrestrial deserts, places characterized by brutal shifts like the Sahara or the Atacama, might experience a variance of 50 or 60 degrees between afternoon and dawn. Mars triples that volatility as its baseline standard at its most hospitable location. If you move away from the equator or look at the global average, the reality becomes even more chilling. The average surface temperature across the entire planet sits at around minus 80 degrees Fahrenheit, or minus 62 Celsius. This means Mars runs roughly 3 times colder than the freezing point of water every single day of the year. Liquid water, the fundamental solvent of all known biology, the matrix in which cellular chemistry occurs, cannot exist on the surface. It freezes solid instantly, locking up the mechanics of life. For an artificial habitat, this permanent freeze-fry cycle creates an unrelenting structural nightmare. A colony cannot simply be insulated. It must be powered by an uninterrupted, massive source of active heat. Every weld, every seal, every layer of composite material must expand and contract under the stress of a 170-degree daily thermal hammer. A single mechanical stutter, a lone heater failure during the night, doesn't result in a cold room. It results in a habitat turning into a cryogenic vault within minutes. Act 3. Beyond the Armstrong threshold. But let us assume you build a structure that can survive the thermal shock waves. You are still left facing a property of the Martian atmosphere that cannot be bargained with, the complete absence of physical pressure. We rarely think about the weight of the air on Earth, but our bodies are structurally designed to exist at the bottom of a heavy gas ocean. The 14.7 pounds per square inch pressing against your skin right now is what keeps your internal fluids in a stable, liquid state. On Mars, that pressure drops to 0.09 pounds per square inch. This is not just a thin atmosphere. It is, for all functional human purposes, a vacuum. This pressure matches the conditions found at 100,000 feet above the Earth, far above the ceiling of commercial flight, well into the stratosphere where the sky turns black and the environment is indistinguishable from open space. There is a precise physical boundary known as the Armstrong limit, which occurs on Earth at about 62,000 feet. It is the altitude where the atmospheric pressure drops so low that the boiling point of water drops to 98.6 degrees Fahrenheit, the exact temperature of the human body. Because Mars sits entirely and permanently above this limit, its entire surface is a zone where unpressurized water cannot remain liquid no matter how warm it gets. If you were to expose liquid water on that 70-degree Martian summer afternoon, it would violently boil away into vapor, driven not by heat, but by the sheer emptiness of the surrounding air. For a human standing unprotected on Mars, the physics of this environment would tear the body apart from the outside in. The moisture on your tongue would instantly flash into gas. The fluid film covering your eyes, the wet linings of your nasal passages, and the delicate membranes inside your lungs would begin to vaporize immediately. Your circulatory system would initially hold together because your blood is contained within a pressurized, elastic loop of veins and arteries. Your blood wouldn't boil in your veins, but every exposed tissue would instantly lose its liquid stability. Worse still is the neurological countdown. Because the Martian air contains almost no oxygen, the pressure differential would actively draw gases out of your blood through your lungs. You wouldn't just be starving for air. Your lungs would run in reverse, stripping oxygen from your bloodstream with every desperate gasp. Consciousness vanishes in about 15 seconds as the brain runs out of fuel. Within 2 minutes, the gases dissolved in your bodily tissues would expand rapidly, causing the body to swell to twice its size as systemic cellular destruction takes hold. This isn't a theoretical calculation. It is a reality verified by tragic decompression accidents in high-altitude aviation and early spaceflight research. The line between life and end on Mars is measured in seconds, and the planet offers no margin for error. Act 4. The poisoned air paradox. It is common to hear sci-fi enthusiasts suggest that we could solve this problem by simply inflating Mars's atmosphere, thickening it until the pressure rises to comfortable levels. But this brings us to the second, independent failure axis of the Martian sky, its chemical identity. The air itself is fundamentally the wrong substance. Earth's atmosphere is a precise, life-sustaining mixture of 78% nitrogen and 21% oxygen, with carbon dioxide existing as a mere trace element at roughly 0.04%. This tiny fraction of carbon dioxide is crucial for our planet's plant life, but it is harmlessly diluted for human lungs. Mars completely reverses this chemistry. Its atmospheric composition is 95% carbon dioxide, 3% nitrogen, 1.6% argon, and a microscopic 0.13% oxygen. To put that 0.13% oxygen figure into perspective, it represents about 1/160th of what human lungs require to function. Even if you were to magically compress the Martian atmosphere until it matched the exact density and pressure of Earth at sea level, the air would remain instantly lethal. Breathing it would be functionally identical to inhaling pure, concentrated internal combustion exhaust inside an unventilated garage. The carbon dioxide would flood your bloodstream, causing immediate hypercapnia, systemic acidosis, rapid loss of consciousness, and end. Thus, Mars defeats human ambition on two entirely separate fronts. If you fix the pressure, the chemistry suffocates you. If you fix the chemistry but leave the pressure low, your fluids vaporize. The two lethalities operate completely independently of one another. Calling the gas layer above Mars an atmosphere is a semantic trick. It is like calling a sheet of plastic a fortress. It provides no protection, holds no breath, and offers no safety. Every single second a human spends on Mars requires a flawless, mechanical barrier to hold back this double-sided atmospheric assault. The habitats we build cannot be thought of as houses or outposts. They must be engineered as static submarines, permanently sealed against an ocean of deadly emptiness and toxic gas. Act 5. The toxic earth underfoot. If you lower your eyes from the lethal sky and look down at the ground, the prospects of colonization turn from atmospheric terror to chemical warfare. The vast, sweeping plains of Mars are covered in a fine, rust-colored material known as regolith. To the casual observer watching rover feeds, it looks like dry desert soil, an alien dirt that could eventually be plowed, fertilized, and farmed inside giant greenhouses. But this material is not dirt. It is a highly reactive chemical hazard. In 2008, NASA's Phoenix lander scooped up samples of the Martian soil near the northern polar region and analyzed its chemical makeup. What it discovered sent a chill through the astrobiology community. The soil is thoroughly saturated with perchlorates, specifically calcium perchlorate, making up roughly 0.5% of the total weight of the surface material. Perchlorates are powerful oxidizers, heavily toxic to human physiology. When introduced into the human body, they aggressively attack the thyroid gland. They do this by mimicking iodine, blocking the thyroid's ability to absorb the actual mineral it needs to produce metabolic hormones. Exposure to perchlorates doesn't strike you down in minutes, like the vacuum of space, but it destroys you slowly and methodically over months and years. It triggers profound hypothyroidism, leading to chronic fatigue, severe metabolic breakdown, cognitive decline, muscle weakness, and the gradual erosion of the body's immune and regenerative systems. And you cannot escape it. The perchlorates aren't confined to an isolated valley or an ancient lake bed. They are distributed evenly across the entire planetary surface, ground into the dust by billions of years of global windstorms. This means the dream of Martian agriculture is fundamentally broken at the root. You cannot simply build a greenhouse, shovel Martian regolith into planters, and sow seeds. Any crops grown in raw Martian soil would absorb the perchlorates, concentrating the toxins within their leaves, roots, and fruit. Anyone eating those plants would be actively poisoning themselves with every meal. To grow food on Mars, every kilogram of soil would first have to undergo an intensive, industrial-scale washing process to leach the perchlorates out. This washing requires massive quantities of liquid water, a resource that is already incredibly scarce on the planet. Furthermore, the runoff from this process doesn't vanish. It becomes a hazardous, highly toxic wastewater stream that requires its own complex chemical treatment facilities to recycle. Every system you build to solve a problem on Mars immediately creates a new compounding resource debt that must be paid in energy, machinery, and time. Act 6. The dust that clings and destroys the chemical toxicity of the soil is only half the nightmare. The physical nature of the dust itself is an inescapable daily antagonist. Because Mars is incredibly dry, and has been subjected to relentless mechanical weathering for eons, its dust has been ground down to an astonishingly microscopic scale. Individual particles are only a few micrometers across, more than 10 times smaller than a strand of human hair, finer and more invasive than talcum powder. Because the Martian atmosphere is so dry and thin, these tiny particles easily accumulate a powerful electrostatic charge. They behave less like sand and more like highly aggressive, microscopic magnets. The moment an astronaut steps outside a habitat, this dust will cling tenaciously to everything it touches: spacesuit fabric, visor materials, mechanical joints, and the delicate rubber seals of airlocks. We already have a historical warning about what extraterrestrial dust does to human explorers. During the Apollo missions to the Moon, astronauts found themselves locked in a constant battle with lunar regolith. Even on short missions lasting only a few days, the sharp, abrasive dust wore down heavy suit fabrics, scratched helmet visors until they were difficult to see through, and jammed critical mechanical seals. When the astronauts returned to their lunar modules, the dust clinging to their suits contaminated the interior air, causing immediate respiratory irritation, coughing fits, and eye inflammation. Now, project that problem onto a Mars colony meant to last for decades. The Martian dust carries a level of chemical toxicity that lunar dust never did. Every time a colonist cycles through an airlock after an extravehicular activity, they will inevitably bring a small amount of dust inside. No matter how many vacuum systems, brushes, or automated air jets you install in the decontamination chamber, the microscopic scale of the particles guarantees that a percentage will breach the habitat's interior. Over months and years, this dust will settle onto interior surfaces and become airborne within the closed ventilation loops. The colonists will breathe it in, day after day, for the rest of their lives. Secrets. We should go there the way we go to Antarctica, as temporary visitors, researchers, and observers, stepping carefully, learning everything we can, and then returning home to the world where we belong. But as a home for humanity, Mars is a dangerous delusion. Every layer of the planet, from its silent, frozen core to its thin, poisonous sky, converges to reject our presence. It is a world that has spent 4 billion years dying, and it will not be remade by our ambition. It will not stretch its gravity to keep our bones strong. It will not spin its core to shield our children from radiation, and it will not soften its air to give us breath. The true lesson of Mars is not that space travel is too difficult, or that our technology has met its match. The lesson of Mars is a profound, grounding message about the absolute uniqueness of the world we already have. It is a mirror that reflects our true place in the universe. It shows us that we are not cosmic nomads who can drift from rock to rock, discarding worlds like used tools. We are the children of Earth. We are structurally, biologically, and neurologically intertwined with the dirt, the air, the gravity, and the living systems of this singular blue planet. As we look out across the cold, silent void toward that small, rusted dot in the distance, our response should not be a desire to conquer, but a profound, overwhelming sense of gratitude for the home we already possess. We live on a masterpiece of cosmic architecture, a world that holds us, breathes with us, and protects us without us ever having to ask. The light of human consciousness was born here, and if it is to survive into the deep future, it will be because we finally learned to ground ourselves in the fragile, beautiful, and infinitely precious world that gave us life. Mars is a desert that will never accept us. Earth is the home that always has. The realization that Mars cannot serve as our planetary evacuation pod changes the very nature of our relationship with the solar system. We are forced to dismantle the science fiction architecture we have built up in our collective imagination over the last century and look at the raw physical constraints of deep space transport. To move beyond the initial phase of flags and footprints, any human presence on Mars must contend with the absolute reality of transit logistics, a problem that begins long before a spacecraft ever encounters the Martian atmosphere. The journey itself is a grueling exercise in human and mechanical endurance. When we discuss traveling to Mars, we are talking about launching a payload into a high-energy trajectory known as a Hohmann transfer orbit. This is not a straight-line sprint. It is an elliptical curving path that uses the Sun's gravity to coast from Earth's orbital path to that of Mars. Because of the laws of orbital mechanics, this transit takes roughly 7 to 9 months each way, depending on the specific alignment of the planets during the launch window. During these 9 months, a human crew is suspended in an environment that is radically different from the surface of either planet. They are exposed to the full, unattenuated blast of deep space cosmic radiation. In low Earth orbit, where the International Space Station resides, the Earth's magnetosphere still provides a significant protective umbrella, deflecting the vast majority of high-energy galactic cosmic rays. In deep space, that umbrella is entirely gone. The crew lives inside a metallic hull that, while engineered to block light solar particles, is virtually transparent to the ultra-high-energy iron nuclei and protons that stream across the galaxy from distant supernovae. As these heavy ions smash through the spacecraft walls, they undergo a process called secondary fragmentation. They collide with the atoms of the ship's aluminum, or composite hull, shattering them and creating a secondary shower of high-velocity neutrons and protons that riddle the interior of the vessel. For 9 months, the astronauts' bodies are subjected to a continuous micro-bombardment at the cellular level. This is not a hazard that can be easily shielded with current propulsion technology. To add enough mass, such as lead or thick water jackets, to completely block these cosmic rays, would make the spacecraft so heavy that no rocket currently conceived could lift it off Earth, let alone accelerate it toward Mars. This radiation environment is compounded by the absolute zero gravity of transit. For nearly 3/4 of a year, the astronauts' musculoskeletal and cardiovascular systems undergo the rapid, unceasing decay of weightlessness. By the time the spacecraft finally approaches Mars, the crew is not a team of high-performing, agile explorers ready to build a new world. They are medically compromised patients. Their bone density has degraded, their muscles have atrophied, their hearts have physically shrunk, and their vestibular systems are completely disoriented. And it is precisely at this moment of maximum physiological vulnerability that they must execute the most dangerous phase of the entire mission: atmospheric entry, descent, and landing. Landing a heavy payload on Mars is an engineering paradox that has plagued aerospace designers for decades. The Martian atmosphere is the worst of both worlds. It is thick enough to generate extreme friction and kinetic heat as a spacecraft plunges into it at over 12,000 miles per hour, requiring massive, heavy thermal protection shields. However, it is far too thin to effectively slow a heavy spacecraft down to a safe landing speed using conventional parachutes alone. On Earth, the dense air allows heavy capsules and returning rocket boosters to utilize parachutes or aerodynamic wings to bleed off the vast majority of their velocity before touchdown. On Mars, a parachute can only do so much. A spacecraft weighing several tons would slam into the rusted plains at supersonic speeds if it relied on parachutes alone. Therefore, any manned Martian lander must utilize a technique called supersonic retropropulsion. The spacecraft must turn itself around while screaming through the thin upper atmosphere and fire massive rocket engines directly into the oncoming supersonic airflow. This requires an astonishing amount of fuel, which must be carried all the way from Earth, adding massive weight to the initial launch. The engineering tolerances during these final 7 minutes of descent are razor-thin. The onboard guidance computers must execute hundreds of split-second adjustments to throttle the engines, stabilize the craft against unpredictable Martian wind shears, and find a flat patch of ground free of boulder fields or steep crater walls. A single sensor glitch, a momentary valve stick, or an asymmetric engine thrust means instant destruction. There is no pilot alive who can manually compensate for these dynamics in real time. The crew is entirely at the mercy of automated software algorithms operating millions of miles away from any human tech support. Once the spacecraft is down and the engines fall silent, the surviving crew steps out into an environment that demands immediate, high-stakes industrial output from individuals who are physically exhausted and radiologically battered. The immediate priority is the assembly of the habitat's life support infrastructure. Every component of this infrastructure must be dragged out of the landing craft and integrated into a functional matrix. The colony cannot survive on internal life support reserves for long. It must immediately begin extracting resources from the local environment to supplement its supplies. This introduces the concept of in situ resource utilization, or ISRU. The cornerstone of every Mars colonization plan is the Sabatier reactor. This is a chemical apparatus that takes carbon dioxide from the Martian atmosphere and reacts it with hydrogen at high temperatures and pressures in the presence of a nickel catalyst. The result of this reaction is methane and water. The methane is intended to be used as rocket propellant for the return journey, while the water is diverted into the colony's life support loops. While the chemistry of the Sabatier reaction is straightforward and has been understood since the 19th century, operating this process on an industrial scale in the middle of a toxic desert is a mechanical nightmare. The Martian atmosphere, while mostly carbon dioxide, is highly contaminated with fine dust particles. If this dust enters the intake valves of the ISRU processing unit, it will quickly abrade the mechanical compressors, coat the chemical catalysts, and clog the delicate filtration membranes. The system requires an incredibly robust, self-cleaning filtration array that can operate continuously without human intervention. Furthermore, the Sabatier reaction requires an initial supply of hydrogen to kickstart the process. Hydrogen is the lightest element in the universe and is notoriously difficult to store for long periods. Over the 9-month transit from Earth, a significant percentage of the liquid hydrogen supply will inevitably boil off and leak through the atomic structure of even the most advanced composite storage tanks. If the colony loses too much hydrogen during transit, the ISRU system cannot function, leaving the astronauts stranded without the propellant required to ever leave the planet. This operational vulnerability highlights the absolute lack of systemic resilience inherent in an alien outpost. On Earth, our industrial systems are webbed with redundancy and fallback options. If a manufacturing plant loses power, it draws from a regional electrical grid. If a water line breaks, trucks can transport water from a neighboring county. On Mars, the colony is a single isolated node in a vacuum. Every critical system, from the nuclear reactors providing electricity, to the ISRU units generating fuel, to the oxygen scrubbers inside the habitat walls, is an absolute single point of failure for the entire population. To manage this risk, the colony's software architecture must be designed with an unprecedented level of autonomous diagnostic capability. The habitat must be treated as a living, thinking organism that constantly monitors its own internal health. Thousands of sensors must track air pressure, temperature gradients, chemical compositions, structural strain, and electrical loads across millions of data points every second. If a minor anomaly is detected, such as a slow microleak in an auxiliary coolant loop, the system must be capable of automatically isolating the failure, rerouting power, and deploying robotic repair units before the human crew even becomes aware of the problem. But robots themselves are not immune to the hostility of Mars. The physical environment of the red planet is a relentless destroyer of machinery. The combination of extreme sub-zero temperatures and fine, abrasive dust creates a wear and tear profile that defies conventional terrestrial engineering. Mechanical joints, bearings, and gears must be completely sealed against the microscopic dust particles. If even a tiny fraction of a percent of Martian regolith slips past a rubberized seal, it acts as an abrasive polishing paste, grinding down steel teeth and seizing electric motors within weeks. The extreme thermal cycling exacerbates this mechanical stress. Every single day, as the temperature swings from a tolerable afternoon high down to a cryogenic nighttime low of -100 degrees, the metallic components of the rovers, solar arrays, and habitat structures expand and contract. This constant mechanical breathing induces severe thermal fatigue along structural welds, electrical connections, and material interfaces. Copper wires become brittle and snap. Solder joints develop microscopic fractures that disrupt data lines. Composite materials delaminate as their constituent layers expand at different rates. This means that a massive portion of the colony's human labor pool must be dedicated entirely to preventative maintenance and active repair work. The astronauts cannot spend their days exploring the planet or conducting breakthrough scientific research. They will spend their lives as grease monkeys, working in cramped, pressurized maintenance bays, scrubbing toxic dust off gaskets, resoldering broken circuit boards, and replacing worn-out actuators. They are locked in a desperate war of attrition against the physical degradation imposed by the world around them. And this war must be fought with an incredibly limited set of tools. You cannot ship an entire industrial manufacturing sector to Mars. The colony will be completely dependent on its ability to manufacture spare parts on site using advanced manufacturing techniques like metal 3D printing. However, 3D printing requires highly purified, consistent raw material feedstocks, powders of titanium, stainless steel, or high-grade polymers. If the printing machines run out of these specialized feedstocks, or if a specific component requires a manufacturing tolerance that a portable 3D printer cannot achieve, the colony is paralyzed. They must wait years for a resupply ship, hoping that the degraded system doesn't experience a cascading failure in the meantime. The medical realities on the ground present an equally grim picture of long-term sustainability. Beyond the macro effects of radiation and low gravity on the bones and heart, the Martian environment attacks human health at the cellular and genetic levels. The continuous background dose of galactic cosmic rays that penetrates the habitat's 3-meter regolith shield, while lower than the unprotected surface, is still significantly higher than anything experienced on Earth. This chronic low-level radiation exposure causes a steady accumulation of double-strand DNA breaks inside the body's cells. When a cell attempts to repair a double-strand break in its genetic code, it often makes mistakes, inserting or deleting base pairs incorrectly. Over years of residency on Mars, the colonists' genomes will become thoroughly riddled with these somatic mutations. This genetic drift drastically accelerates the aging process, triggers early-onset cataracts, and causes a massive spike in the incidence of aggressive, treatment-resistant cancers. The colony's medical facilities must be engineered to function as a highly advanced oncology and surgical center. But performing complex medical procedures or surgeries on Mars is complicated by the gravity environment. In 38% gravity, the behavior of fluids inside an operating room is radically altered. Blood does not pool or flow the way it does on Earth. It can form floating droplets or cling to surgical instruments via surface tension, creating a high risk of biological contamination inside the sterile field. The healing process itself is also compromised. Because low gravity disrupts the normal circulatory pressure gradients, the delivery of oxygen and immune cells to wound sites is slowed, leading to prolonged recovery times and a severely elevated risk of post-operative infections. The psychological weight of this medical vulnerability can induce a state of chronic, low-level panic among the population. On Earth, if you suffer a severe medical emergency, such as a stroke, an acute appendicitis, or a complex compound fracture, you are usually within minutes or hours of a specialized trauma center staffed by dozens of experts with access to an infinite supply of blood plasma, antibiotics, and surgical hardware. On Mars, your medical staff consists of perhaps 2 or 3 doctors who must share a tiny, multi-purpose clinic room. If you require a rare pharmaceutical agent or a highly specialized piece of medical equipment that wasn't included in the initial launch manifest, there is nothing the doctors can do. You are fundamentally on your own, facing the reality that a minor, easily treatable terrestrial illness can become a terminal event on the red world. This existential isolation alters the very nature of human social structures within the colony. A Mars outpost cannot function as a free, democratic society in the way we understand it on Earth. It must be governed by a strict, semi-military hierarchy, where individual liberty is completely subordinated to the operational needs of the life support system. In a world where a single open valve or an unauthorized consumption of power can kill the entire community, there is no room for dissent, personal eccentricity, or non-compliance. Every aspect of an individual's life, their daily caloric intake, their water usage, their work schedule, their sleep patterns, and even their reproductive choices must be tightly monitored, regulated, and optimized by central management algorithms. The colony must operate as a closed, command economy where resource efficiency is the ultimate moral law. If an individual becomes chronically ill, injured, or psychologically unstable to the point where they can no longer contribute to the physical maintenance of the habitat, they transform from an asset into a massive, resource-draining liability. The ethical pressure this reality places on both the individual and the community leadership is profoundly disturbing. Hard decisions regarding the allocation of scarce medical supplies or life support resources will inevitably arise, forcing the colony to adopt a ruthless utilitarian survival matrix that is completely incompatible with the human rights frameworks we take for granted on Earth. The dream of terraforming Mars, the grand vision of warming the planet, melting the polar caps, and thickening the atmosphere over centuries until humans can walk the surface without spacesuits, is revealed to be an astronomical impossibility when confronted with the actual inventory of the planet's volatile elements. For decades, sci-fi authors and planetary scientists have hypothesized that if we could find a way to trigger a runaway greenhouse effect on Mars, we could unlock enough trapped carbon dioxide to create a thick, warm sky. However, comprehensive planetary surveys conducted by modern orbital missions have delivered a devastating verdict. There is simply not enough carbon dioxide left on Mars to achieve this. If we were to deploy every conceivable technology, from detonating thermonuclear devices over the ice caps to redirecting carbon-rich asteroids to slam into the surface, the total amount of carbon dioxide that could be realistically liberated would only raise the atmospheric pressure from 0.6% of Earth's to about 7%. While 7% is a massive increase in absolute terms, it is still a near vacuum. It is still well below the Armstrong limit. Your bodily fluids would still boil at your body temperature. The sky would remain black, the radiation would still scream down unimpeded, and you would still die within 2 minutes without a fully pressurized spacesuit. The vast majority of the atmosphere that Mars possessed in its youth did not get absorbed into the rocks or frozen into the soil. It was completely stripped away by the solar wind and lost to the interstellar void billions of years ago. The gas is gone, and no amount of human engineering can call it back. Furthermore, even if we could somehow import trillions of tons of volatile gases from the outer solar system, perhaps by mining the moons of Jupiter or Saturn and shipping them to Mars, the planet would still lack the fundamental property needed to hold on to them, a planetary dynamo. Because Mars's interior is cold and dead, any atmosphere we artificially inject into the system would be immediately subjected to the same solar stripping process that destroyed the original sky. Without a global magnetic shield to deflect the solar wind, the sun would simply continue to sandblast the upper atmosphere, bleeding our imported gases back into space across geological time. We would be attempting to fill a bucket that is riddled with holes, engaging in a permanent, multi-generational thermodynamic maintenance campaign that would consume the entire industrial output of human civilization just to keep the sky from disappearing. This reality forces us to look at the concept of space exploration through a much more mature and grounded lens. The value of Mars is not that it is a destination for human habitation, but that it is a profound scientific laboratory. It is a time capsule from the dawn of the solar system. Because Mars has no plate tectonics, no active liquid water cycle, and no sprawling biosphere to constantly chew up and remodel its crust, its surface rocks have remained virtually unchanged for billions of years. By studying the geology of Mars, we are looking directly at the conditions that existed in the early solar system when life was first emerging on Earth. It holds the answers to some of the most fundamental questions we can ask. Is life a common cosmic imperative that emerges whenever water and organic chemistry mix, or is it an exceedingly rare, fragile fluke? Did Mars once harbor its own independent genesis of life during its warm, wet youth? And if so, did that life die out when the core froze? Or does it still survive today, deep within the dark, damp fractures of the subterranean crust? These are questions of immense philosophical and scientific consequence, and they can be answered without sending millions of colonists to live in underground bunkers. Our robotic rovers, landers, and automated sample return missions are becoming exponentially more sophisticated with every passing year. We can explore the ancient lake beds of Jezero Crater, drill into the ice sheets of Arcadia Planitia, and analyze the chemical signatures of Martian methane plumes using machines that do not require oxygen, do not absorb radiation damage, do not suffer from bone density loss, and do not experience psychological despair. When we look at the staggering cost of trying to force a human population to survive on Mars, we realize that those resources are infinitely better spent elsewhere. The multi-trillion-dollar expenditure required to keep a few hundred people alive in a permanent state of high-stakes crisis on the Red Planet could fund a golden age of scientific discovery across the entire solar system. We could build fleets of space telescopes capable of mapping the atmospheres of thousands of exoplanets in nearby star systems, searching for the true chemical signatures of distant biospheres. We could send deep-diving robotic submarines to explore the hidden liquid oceans beneath the ice crusts of Europa and Enceladus, places that are far more likely to harbor active, living, extraterrestrial ecosystems than the irradiated sands of Mars. And most importantly, those resources can be deployed to stabilize and secure the only true home we will ever have. The push for Mars colonization is often driven by a form of technological defeatism, the subconscious belief that our social, political, and environmental problems on Earth are so intractable that our only hope is to start over from scratch on a blank canvas. But Mars is not a blank canvas. It is a toxic, frozen cage. The idea that we can engineer our way out of a hostile environment on Mars while failing to engineer our way out of climate shifts, resource scarcity, or environmental degradation on Earth is a profound paradox. The atmospheric adjustments required to stabilize Earth's climate are minor tweaks compared to the planetary-scale industrial transformations that would be needed to make even a single square mile of Mars habitable for an unpressurized human being. Our home planet is an exquisite anomaly in the cosmos. It sits at the precise distance from its star to maintain liquid water across its entire surface. It possesses a dynamic, living core that wraps it in a protective magnetic field. It features a thick, rich nitrogen-oxygen sky that allows us to walk naked under the sun, to feel the wind on our skin, and to breathe without the mechanical hiss of an oxygen pump. Every breath we take, every drop of water we drink, and every plant that grows out of our soil is a testament to a complex, multi-billion-year ecological loop that supports us automatically, completely free of charge. To view this world as a stepping stone, a temporary launching pad to be discarded once we develop sufficiently powerful rockets, is a profound failure of cosmic perspective. There is no escape hatch in the night sky. There is no second chance waiting for us among the stars. The dead deserts of Mars are not an invitation to build a new civilization. They are a stark, terrifying warning of what a planet looks like when it loses its life support systems. Our destiny is not to turn Mars into a broken, high-maintenance copy of Earth, but to ensure that the magnificent, irreplaceable world we already inherit remains a living sanctuary for generations to come. We must turn our gaze back downward, away from the rusted illusions of the Red Desert, and commit ourselves to the preservation of the only miracle we know to exist in the vast, silent emptiness of space. The logistical fantasy of Mars colonization becomes even more apparent when we examine the actual physics of returning home. The architecture of a true colony cannot be a one-way conveyor belt of human capital. There must be a viable, reliable method for vehicles to lift off from the Martian surface and make the journey back to Earth. This requirement introduces a completely new set of mechanical and chemical hurdles that dwarf the challenges of landing. To leave Mars, a spacecraft must overcome the planet's gravitational well, while Martian gravity is only 38% of Earth's. Escaping its pole still requires a velocity of approximately 5 kilometers per second, or roughly 11,000 miles per hour. Achieving this speed requires an immense amount of thrust, which in turn requires hundreds of tons of liquid propellant. Because launching this return fuel directly from Earth would make the initial outbound rockets impossibly heavy, every realistic mission profile relies entirely on the assumption that the return propellant will be manufactured on the surface of Mars using the automated, in-situ resource utilization factories. This means that long before a human crew ever lifts off from Earth, an uncrewed automated fleet must land on Mars, deploy massive solar or nuclear power arrays, activate chemical processing reactors, and run continuously for over 2 years just to fill the return propellant tanks. The spacecraft that the astronauts will eventually use to go home must sit out on the open, windswept plains of Mars for years, completely unattended, enduring the brutal thermal cycles, the corrosive chemistry of the perchlorate dust, and the unrelenting bombardment of solar radiation. During this extended staging phase, the vehicle's vital systems are highly vulnerable to degradation. Liquid methane and liquid oxygen, the preferred propellant combination for modern Mars architectures, must be kept at extreme cryogenic temperatures. If a single auxiliary cooling unit suffers a mechanical breakdown, or a solar panel array becomes completely covered in fine dust during a global storm, the system will lose power. The cryogenic propellants will begin to warm, boil off, and vent out into the thin atmosphere. A colony could find itself in a position where their ticket home has literally vaporized into the sky, leaving them stranded with no way to replenish the lost fuel before their life support supplies run out. Furthermore, launching a rocket from the surface of Mars is fundamentally different from launching a rocket from Cape Canaveral or the Kennedy Space Center. On Earth, a launch is supported by an infrastructure of thousands of specialized technicians, real-time diagnostic telemetry centers, launch pads equipped with massive water suppression systems to absorb destructive acoustic shock waves, and cleanroom facilities to handle delicate components. On Mars, the launch pad is a raw patch of compacted desert ground. There are no gantry cranes to perform last-minute structural inspections, no specialized crews to fix a stuck fuel valve, and no backup components if a sensor fails during the terminal countdown. When the engines ignite, the tremendous heat and kinetic force of the exhaust plume will interact violently with the local environment. The superheated rocket exhaust will instantly vaporize any subsurface ground ice beneath the launch zone, creating explosive pockets of high-pressure steam that can crack the launch pad and destabilize the vehicle. Simultaneously, the force of the blast will kick up millions of sharp, electrostatically charged regolith particles, creating a localized, supersonic dust cloud that will sandblast the exterior of the ascending spacecraft, potentially damaging thermal protection tiles, pitting windows, and clogging aerodynamic sensors. If the rocket successfully clears the atmospheric haze and achieves orbit, the crew enters yet another 9-month transit through the deep space radiation void. By the time they finally return to Earth, their bodies have undergone nearly 2 full years of cumulative physiological erosion. The combination of prolonged low-gravity exposure on Mars, zero-gravity exposure during transit, and continuous radiation damage leaves the returning astronauts in a state of profound medical fragility. They are no longer the peak physical specimens who left the planet. They are individuals with severely degraded immune systems, microfractured bones, atrophied hearts, and altered neurological profiles. This physiological cost highlights the complete impracticality of treating Mars as a workplace or an industrial frontier. On Earth, if an individual takes a job at a remote mining outpost in the Arctic or an oil rig in the North Sea, they endure harsh conditions and isolation for a few months at a time, but they return home with their health intact and their biology unaltered. A tour of duty on Mars represents a permanent, structural downgrade to the human vehicle. The damage accumulated during a single mission lifecycle is so severe that it would likely preclude an individual from ever making the journey a second time. Mars is an environment that permanently uses up the human beings who enter it. This reality fractures the economic model of space commercialization. The modern tech industry narrative suggests that private corporations will eventually colonize Mars by driving down launch costs through reusable rocket architectures and economies of scale. But this view ignores the fact that transportation is only a fraction of the cost equation. The true expense of a Mars colony lies in the permanent operational overhead of keeping humans alive in an environment that provides absolutely nothing for free. On Earth, nature provides an infinite infrastructure of ecosystem services. A corporation building a factory or a city does not have to include the cost of manufacturing air, filtering the entire water supply of the population from toxic chemicals, or burying the entire corporate campus under 10 feet of concrete to prevent the workers from developing terminal radiation sickness. The environment of Earth does 99% of the economic work required to sustain human labor. On Mars, that economic balance sheet is completely inverted. The corporation or government must pay for every single milliliter of oxygen, every calorie of food, every watt of heat, and every gram of structural shielding. The cost of maintaining human labor on Mars is thermodynamically negative. It requires a continuous infusion of energy and capital that can never be offset by any industrial or resource output the planet can produce. This economic sinkhole ensures that any human presence on Mars will remain small, fragile, and entirely dependent on the political whims of the home planet. It can never transition into a sovereign, self-sufficient society because it can never break its dependency on the industrial supply chains of Earth. The colony will always be one missing shipment of specialized computer chips, one broken valve manufacturing contract, or one terrestrial political budget cut away from complete systemic collapse. When we look deeply into the mechanics of this planetary trap, we begin to understand why the cosmic silence of the universe is so profound. For decades, astronomers and physicists have pondered the Fermi paradox, the troubling question of why. Given the billions of star systems in our galaxy and the billions of years of cosmic time, we see no obvious signs of advanced extraterrestrial civilizations or interstellar empires. The harsh reality of Mars provides a compelling answer. Perhaps the physical laws of the universe contain a built-in checkpoint for intelligent life. It is relatively easy for a species to develop technology, exploit the resources of its home world, and take its first tentative steps into space using chemical rockets. But the jump from living on a perfectly tuned biosphere to colonizing a dead, irradiated rock is not a linear step up in technological difficulty. It is a categorical cliff. The thermodynamic barriers, the biological constraints of low gravity, the genetic destruction of cosmic radiation, and the compounding vulnerabilities of closed-loop life support systems may represent an insurmountable wall for any biological species. The universe does not appear to be an open frontier waiting for galactic empires to carve their names into the stars. It appears to be an ocean of beautiful, highly isolated sanctuaries, separated by vast, unyielding distances of lethal emptiness. We are not cosmic conquerors destined to outgrow our home. We are the specialized caretakers of a singular planetary miracle. The rusted plains of Mars are not a canvas for our future, but a monument to the absolute finality of planetary end. They show us what happens when a world loses its core, loses its sky, and turns its back on the possibilities of life. The ultimate value of our journey to the Red World is not that we will find a place to build a new home, but that we will finally learn to appreciate the one we already have. When we look at the lifeless sands of Mars through the visors of our spacesuits, we are meant to feel a profound, overwhelming sense of relief that we can turn around, board our ships, and return to a world that holds us, breathes with us. These ultrafine perchlorate-laced particles will penetrate deep into the alveolar sacs of the human lungs, where they cannot be easily cleared. The long-term medical consequences of breathing a steady dose of toxic, electrostatically charged alien dust over a lifetime are completely unknown. There is no historical population to study. But no doctor or toxicologist would view this scenario as anything less than a slow-motion health catastrophe. The very ground the colony sits upon is a passive weapon, slowly invading the lungs and destroying the thyroids of the people who dare to walk on it. Act 7. The crushing arithmetic of water mining. Every vision of a self-sustaining Mars colony relies on the assumption that we can harvest the resources already present on the planet. Foremost among these is water. A human being requires 2 to 3 liters of water daily just to survive. When you factor in the additional water needed for food preparation, basic hygiene, sanitation, clothes washing, and equipment maintenance, that number skyrockets to roughly 50 liters per person per day to maintain a functional community. On Earth, we are completely insulated from the logistical reality of this demand. Our planet features an automated global hydrologic loop. Solar energy evaporates the oceans, clouds form, rain falls, and aquifers refill. The planet does 100% of the heavy lifting. Mars has no water cycle. There are no clouds delivering rain, no rivers cutting through the valleys, and no accessible liquid tables beneath the sands. Every single drop of water a Martian colony requires must be violently extracted from frozen, ancient reserves through sheer industrial effort. Mars does possess water, but it is locked away in forms that resist easy harvesting. The most obvious reservoirs are the polar ice caps, but these are located at extreme, hypercold latitudes where survival is even more difficult and solar energy is practically non-existent for half the year. Furthermore, this ice is not pure. It is a frozen matrix of water ice intimately intermixed with solid carbon dioxide, dry ice, at temperatures that make the material as hard as granite. To extract clean water from a polar cap, a colony would need to establish a massive, automated mining operation capable of crushing this super-chilled ice, heating it to sublimate away the carbon dioxide, melting the remaining water ice, condensing the vapor, and then running it through multi-stage purification arrays. Every single phase of this process demands an enormous, continuous supply of electrical and thermal energy. The alternative is to mine ground ice, which sits buried beneath layers of regolith at mid to high latitudes. But as you move closer to the equator, where a colony would actually want to build to take advantage of warmer temperatures and better solar power potential, the ground ice thins out and completely vanishes. If you build where the water is, you freeze and lose your solar power. If you build where the sun is, you must transport your water across hundreds of miles of trackless, hazardous terrain. This absolute scarcity transforms recycling into an unforgiving religion. On the International Space Station, a highly advanced water recovery system captures sweat, ambient humidity, and urine, processing it back into pristine drinking water. This system achieves an impressive 93% efficiency rate. But when you scale that up to a modest Martian colony of just 100 people, the missing 7% becomes a terrifying deficit. At 50 liters per person daily, a 100-person colony circulates 5,000 liters of water through its life support systems every day. A 7% loss means that 350 liters of water are permanently lost to the system every 24 hours through filtration waste, system leaks, and structural venting. That is 350 liters that must be replaced by fresh mining operations, day after day, 365 days a year. That totals over 127,000 liters, or 127 metric tons, of fresh water that must be dug out of the frozen Martian crust annually just to keep 100 people alive at a baseline level. And this number doesn't include a single drop for agriculture. The moment you introduce hydroponic bays or vertical farms to grow food, your water demand multiplies by orders of magnitude. Water on Mars is not a resource you find. It is an endless, high-energy industrial campaign that can never take a single day off. Act 8. The end of the planetary dynamo. To fully comprehend why Mars is so utterly broken, you have to look deeper than its surface, past its frozen crust, down into the very heart of the planet. The ultimate source of Mars's hostility is not its distance from the Sun or its chemical composition. It is a failure of planetary geometry. Mars is simply too small. Earth is a large, dynamic world with a restless interior. Deep beneath our feet, the immense heat left over from our planet's formation, combined with radioactive decay, keeps the outer core of iron and nickel in a state of constant, turbulent churning. This liquid metal movement functions exactly like a massive electrical generator, creating a phenomenon known as the planetary dynamo. This dynamo generates the magnetosphere, a vast, invisible magnetic shield that wraps around the Earth, extending far out into space. This magnetic shield is our ultimate line of defense. When the sun unleashes its ferocious solar wind, a relentless torrent of highly energetic, charged particles traveling at millions of miles per hour, the magnetosphere catches them and deflects them safely around the planet. What little radiation manages to slip through this magnetic defense is absorbed by our dense atmosphere. Together, these two systems drop the radiation dose at Earth's surface to a benign background level of about 2 to 3 millisieverts per year. Mars has neither of these shields. Billions of years ago, a young Mars did possess a liquid churning core and a powerful magnetic field of its own. We can still see the magnetized signatures etched into the ancient rocks of the southern Martian highlands, a ghost of the planet it used to be. But because Mars has only about half the diameter and 1/10 the mass of Earth, it has a much higher surface area to volume ratio. It radiates its internal heat out into space far faster than a larger planet can. As a result, early in its history, Mars ran out of interior heat. Its core cooled, solidified, and the planetary dynamo ground to a permanent halt. The magnetic field collapsed. Once that shield vanished, Mars was left completely naked before the sun. The solar wind struck the upper atmosphere directly, systematically stripping away the gas molecules, atom by atom, over hundreds of millions of years. Mars didn't lose its atmosphere to a singular cosmic disaster. It bled its air into the vacuum of space across geological time because it was too small to retain the magnetic armor needed to protect it. Act 9. The unfiltered sky. Because of the end of its core, the modern Martian surface is bathed in a perpetual, invisible downpour of lethal radiation. It receives the full, raw output of both the sun's solar particle events and the highly penetrating cosmic rays originating from deep space. The thin carbon dioxide atmosphere provides less than 1% of the shielding capacity of Earth's sky, allowing these particles to strike the ground completely unimpeded. We don't have to guess at the severity of this radiation environment. NASA's Curiosity rover carried a sophisticated radiation assessment detector specifically to measure the dosage a human explorer would absorb on the surface. The data returned was alarming. During a period of solar minimum, when the sun is at its quietest and safest, the surface radiation dose averaged roughly 24 millisieverts per month. Over the course of a year, an individual living on Mars would accumulate approximately 290 millisieverts of radiation. To understand how catastrophic that number is, you have to look at terrestrial safety standards. In most industrialized nations, the absolute maximum annual radiation dose permitted for a professional radiation worker, such as a nuclear power plant technician or a medical radiologist, is 20 millisieverts. A Martian colonist would smash through that annual safety limit in less than 4 weeks, simply by sitting inside their habitat doing absolutely nothing. By the end of their first year on the red planet, an explorer would have absorbed nearly 15 times the maximum legal annual limit allowed for the most exposed workers on Earth. And this is merely the baseline condition. The sun is an unstable star, prone to unleashing massive solar particle events, coronal mass ejections that hurl billions of tons of high-energy protons into space. On Earth, our magnetosphere deflects these storms. On Mars, a major solar particle event can strike the surface and deliver several hundred millisieverts of radiation in a matter of hours. It is the radiological equivalent of standing in front of an unshielded nuclear reactor core for an afternoon. The biological consequences of this exposure are severe and multi-generational. it drastically elevates the lifetime risk of aggressive cancers. It damages the central nervous system, accelerating neurodegenerative conditions and impairing cognitive function over time. It attacks the body's reproductive cells. Temporary or permanent sterility is a highly probable outcome for anyone exposed to these levels of cumulative dosage. If colonists do manage to conceive children, the risk of genetic mutations being passed down to the next generation escalates dramatically, alongside a steep rise in the probability of severe birth defects. A colony cannot survive if it cannot safely reproduce. Mars's radiation doesn't just threaten the brave individuals who volunteer for the first missions. It strikes directly at the biological viability of their children, threatening to mutate and degrade the community before it can even establish a foothold. Act 10. The 50,000-kilogram roof. There is an obvious, brutal engineering solution to this radiological assault. You must bury the colony. The physics is undeniable. If you put enough mass between yourself and the sky, the radiation particles will be absorbed before they can hit your cells. The standard blueprint for a Martian habitat involves taking the local regolith and piling it on top of the structures to create a thick, protective earthen shield. To bring the internal radiation levels down to something resembling Earth's safe background standard, you need a layer of Martian regolith approximately 3 meters, roughly 10 feet, thick, covering every square inch of the habitat's roof and walls. The math behind this solution is perfectly sound, but when you translate that math into physical engineering on an alien world, the numbers turn into a structural nightmare. Martian regolith is heavy, possessing a density of about 1.5 grams per cc. When you stack that material 3 meters deep over a surface, it exerts a downward physical force of roughly 500 kilograms per square meter, which translates to nearly 9,000 pounds of crushing weight pressing down on every single square foot of your ceiling. Imagine a modest, basic habitat module with a floor space of 100 square meters, roughly the size of a small 2-bedroom apartment. To shield just the roof of this single module, you would need to pile on approximately 450,000 kilograms of loose, toxic dirt. That is nearly 500 tons of dead weight, resting on top of a structure that must simultaneously fulfill several other wildly conflicting engineering demands. This habitat must be airtight, holding in a pressurized internal atmosphere against the near vacuum of the outside world. It must be perfectly insulated against a 170-degree daily temperature swing, and it must now support a 500-ton ceiling of loose, abrasive material without bowing, cracking, or fatiguing over decades. A single structural failure, a tiny micro-fissure caused by the shifting weight of those 500 tons, would result in an instantaneous blowout of the internal atmosphere, causing immediate decompression and end for everyone inside. Furthermore, moving 500 tons of material on Mars is a Herculean industrial task. There are no diesel-powered construction cranes waiting on the launch pad. There are no heavy bulldozers or earth movers idling in a Martian depot. Every single gram of heavy machinery must be launched from Earth at astronomical expense, landed safely through a thin atmosphere that defies heavy payloads, and then continuously maintained in an environment where the dust jams every gear and the cold freezes every lubricant. A crew of astronauts, restricted by bulky, pressurized spacesuits that limit mobility and increase fatigue, would have to manage this massive excavation project by hand or via remote-controlled rovers. What takes a few weeks on a standard Earth construction site would translate into months or years of hazardous, exhausting labor on Mars, all while the crew is actively absorbing their radiation dose before the shield is completed. The alternative often discussed in space architecture is to abandon the surface entirely and seek shelter inside Mars's lava tubes, vast, underground volcanic caverns left behind by the planet's ancient geologic past. These natural caves would indeed provide excellent, ready-made radiation shielding without the need to move millions of tons of Earth. But the underground introduces its own distinct set of hazards. Excavating and sealing a raw, subterranean volcanic cavern is an unproven and incredibly complex engineering feat. Drilling into these basaltic structures would generate immense clouds of fine, sharp dust, immediately saturating the construction area with the very perchlorates and respiratory hazards the colonists are trying to avoid. In an enclosed, underground environment, air circulation and filtration become even more critical and difficult to manage. There are no free passes on Mars. Every choice you make, whether you stay on the surface or hide beneath it, simply forces you to trade one lethal atmospheric or environmental crisis for another. Act 11. The Fragile Mirror. When we tally up the true cost of Mars, we find a world that does not possess a single redeeming environmental quality for human physiology. It is a planet that ran out of internal heat before we did, losing its magnetic shield, sacrificing its atmosphere to the solar wind, and leaving its surface exposed to a lethal cocktail of radiation, vacuum, and sub-zero temperatures. Its soil is a toxic trap, its dust is a lung-shredding poison, and its water must be fought for with heavy machinery every single day. Mars is not a backup planet. It is a dead end wrapped in an illusion. The more deeply we analyze the data sent back by our rovers and landers, the more clearly we see that the dream of expanding humanity across the red world is an act of profound cosmic hubris. We have mistaken the presence of solid ground for the presence of a home. This realization forces us to look back across those 142 million miles of empty space toward the world we already inhabit. Earth is not just a planet. It is a spectacular automated life support miracle. Its core churns to wrap us in a magnetic embrace. Its thick nitrogen-oxygen sky holds our pressure, cushions our temperatures, filters our radiation, and automatically cycles our water through a perfect, self-replenishing loop. We live on a world that has spent billions of years fine-tuning itself to support our biology. To treat this planet as disposable, to look at Mars as a fallback plan that will save us from our environmental failures at home, is a terrifying delusion. If we possess the advanced technology, the trillions of dollars, and the generational willpower required to build heavy industrial underground cities on a radioactive desert world that actively tries to kill us every second, then we possess more than enough power to preserve, protect, and heal the breathtakingly beautiful, breathable world we already have. Mars shows us what happens when a planet dies. Our job is not to join it in the graveyard, but to make sure our own home never takes that first, irreversible step into the cold. Act 12. The Arithmetic of the Greenhouse. The dream of a Martian colony always culminates in a vision of green, vibrant, leaf-filled hydroponic bays and sprawling pressurized greenhouses cutting through the rusted monotony of the landscape. We imagine rows of crops, converting the planet's abundant carbon dioxide into clean, breathable oxygen, while feeding a bustling population. It is a beautiful, intuitive image rooted in our understanding of terrestrial botany. We know plants love carbon dioxide, and Mars has it in spades. But when you step away from the conceptual renderings and sit down with the cold arithmetic of agricultural engineering on an alien world, the green paradise completely evaporates, replaced by a brutal balance sheet of energy and mass. To feed a single human being on a long-term, self-sustaining basis, you cannot rely on occasional harvests or compact garden beds. A human adult, working in the high-stress, physically demanding environment of a Mars colony, requires between 2,500 and 3,500 calories per day. Translating that caloric requirement into plant matter means maintaining roughly 40 to 50 square meters of highly productive, continuously cultivated crop area per person. For a small community of just 100 people, you are looking at nearly 5,000 square meters of agricultural space, an area roughly the size of a professional football field, entirely enclosed within a flawless pressure vessel, heated to terrestrial spring temperatures, and bathed in intense, uninterrupted light. This is where the environment of Mars throws its first major roadblock. As we established, Mars sits so far from the Sun that it receives less than half the solar energy that reaches Earth. But the problem is actually much worse for a farmer. The light that does reach the surface must pass through a thin but incredibly dusty atmosphere. This persistent global haze filters out critical wavelengths of light, meaning that the natural sunlight hitting a Martian greenhouse is far too weak to sustain high-yield, fast-growing crops like wheat, potatoes, or soybeans at the scale required to prevent human starvation. To keep these plants alive and producing at peak efficiency, you cannot rely on windows or transparent domes. You must use artificial grow lights, massive arrays of high-intensity LEDs operating 24 hours a day. The electrical power required to illuminate a football field of crops to the necessary intensity is staggering, measuring in the hundreds of kilowatts of continuous power. And you cannot generate this power with solar panels on the Martian surface. The same weak, dusty sunlight that starves the plants also starves the solar arrays. To keep the lights on through the brutal Martian night, and through the months-long global dust storms that can blot out up to 99% of all surface sunlight, a colony must rely on a continuous, unyielding power source. This means a colony is not an ecological paradise. It is an industrial nuclear outpost. Without a fleet of high-output, space-hardened nuclear reactors running non-stop, the lights go out, the crops fail, and the colony starves within weeks. Act 13. The biotic closed-loop failure. Even if you secure an infinite source of electrical energy to run the grow lights, you are left facing the terrifying volatility of a closed-loop life support system. On Earth, our agricultural systems exist within an open, infinitely buffered biosphere. If a localized crop disease breaks out, or if a specific soil nutrient becomes depleted, the rest of the planet's ecosystem balances the equation. The oceans absorb excess gases, the atmosphere dilutes toxins, and migratory organisms redistribute nutrients. In a Martian greenhouse, the loop is completely closed, incredibly tight, and fundamentally fragile. The air circulating through the plant bays is the exact same air the colonists breathe after it passes through a series of mechanical scrubbers. Plants are not passive food factories. They are dynamic biological organisms that release vast quantities of volatile organic compounds, moisture, and gases into their environment. For instance, during periods of rapid growth, crops produce significant amounts of oxygen. While this sounds ideal for a human colony, an overabundance of oxygen inside a sealed, high-energy environment creates a catastrophic fire hazard. The atmospheric composition inside the habitat must be micromanaged to the decimal point, constantly injecting nitrogen or other inert buffer gases to keep the air from becoming an explosive tinderbox. Conversely, plants also produce trace amounts of toxic gases, like carbon monoxide and ethylene, as natural byproducts of their metabolic cycles. In the open air of Earth, these gases disperse into insignificance. Inside a sealed 5,000 square meter capsule, they accumulate rapidly. Without incredibly complex, high-maintenance catalytic oxidizers running continuously to strip these trace toxins from the air, the plants will literally poison themselves, and the human beings living downstream from their ventilation loops. Then there is the issue of biological waste. To maintain a true closed loop, every gram of organic material must be recycled. This means human waste and inedible plant matter, stems, roots, and leaves, must be broken down and converted back into nutrient-rich fertilizer for the next crop cycle. On Earth, this process is handled by a subterranean army of billions of bacteria, fungi, insects, and worms working across millions of acres of soil. Replicating this complex multi-tiered decomposition ecosystem inside a sterile mechanical facility on Mars is a nightmare of bioengineering. If you introduce the wrong strain of bacteria, or if a single pathogen mutates inside the warm, closed environment of the greenhouse, it can rip through your monoculture crop supply in days. On Earth, a crop failure is a financial disaster. On Mars, where the next resupply ship is 142 million miles away and takes 8 months to arrive, a crop blight is an end sentence for the entire population. Act 14. The psychology of the permanent submarine. Let us look past the physical infrastructure of pumps, reactors, and grow lights, and turn our attention to the internal landscape of the human mind. The conversation around Mars colonization is dominated by aerospace engineers, orbital mechanics, and materials scientists, people who view the problem through the lens of structural tolerances and delta V. But the most fragile component of any Martian colony is not the hull of the habitat or the seals on the airlocks. It is the psychological architecture of the human beings trapped inside them. To live on Mars is to volunteer for a life of permanent, unyielding sensory deprivation. Think about the sensory canvas of your daily life on Earth. The rustle of wind through a canopy of trees. The smell of damp earth after a rainstorm. The shifting patterns of clouds across an infinite blue sky. The feeling of natural sunlight warming your bare skin. The sound of breaking waves on a shoreline. These are not merely aesthetic pleasantries. They are the evolutionary baseline of the human nervous system. Our brains, our vision, our hormonal balances, and our psychological coping mechanisms evolved across millions of years to interpret and respond to the rich, chaotic, open environment of a living world. Mars offers none of this. To be a citizen of a Martian colony is to live out your entire existence inside a permanent submarine buried under 10 feet of loose dirt. Your visual world will be defined by the harsh, monochromatic glare of LED lighting, the cold metallic curves of structural bulkheads, and the hum of ventilation fans that can never, ever be turned off. If you are permitted to look outside at all through a heavily shielded, thick-paned window, you will see a flat, unmoving desert of rust-colored dust beneath a dim butterscotch sky. Nothing moves, nothing grows, nothing changes. The concept of a walk outside is forever altered. You cannot simply step out your front door to clear your head. To leave the habitat requires a grueling, 45-minute checklist of pre-breathing oxygen to prevent decompression sickness. Donning a heavy, restrictive 70-kilogram life support suit, checking dozens of seals, and cycling through a mechanical airlock. And when you finally stand on the surface, you are still trapped. You are trapped inside a helmet, looking through a thick visor, hearing only the mechanical hiss of your suit's oxygen pump and the sound of your own breathing. The landscape does not welcome you. It threatens you with immediate, catastrophic end if a single layer of your suit's composite fabric should tear on a sharp volcanic rock. This total isolation from nature triggers a profound, slow-motion psychological erosion that space psychologists refer to as Earth out-of-view phenomenon. During long-duration missions on the International Space Station, astronauts can always look out the cupola window and see the giant, brilliant blue marble of Earth spinning beneath them. It is a powerful, grounding, emotional anchor. On Mars, Earth is reduced to a tiny, cold blue dot in the night sky, indistinguishable from any other star. The psychological realization that you are completely abandoned on a dead rock, separated from everything that created your species by a void so vast that light itself takes 20 minutes to cross it, creates a sense of profound, existential vertigo. In such an environment, interpersonal friction becomes explosive. In a small group of people, confined to a claustrophobic, underground space with no escape, minor annoyances transform into deep, pathological animosities. You cannot walk away from someone you despise when the wall behind them is the only thing keeping the vacuum of space from boiling your blood. Act 15. The medical decay of low gravity. Even if you assemble a crew of psychologically flawless individuals who can withstand the crushing isolation of the Martian underground, you cannot escape the quiet, systemic betrayal of the planet's gravitational field. Mars is a small world, and with its reduced mass comes a gravitational pull that is only 38% of what we experience on Earth. If you weigh 150 pounds on Earth, you will step onto the Martian scales and see a mere 57 pounds. Initially, this sounds like a delightful novelty. We imagine leaping across craters, lifting heavy pieces of equipment with ease, and moving with an effortless, bounding grace. But to the human body, gravity is not just a force that keeps our feet on the ground. It is a fundamental biological signal. Every organ, every bone, Every blood vessel and every cell in our bodies is hardwired to operate against the constant, unrelenting resistance of a one-gravity environment. When you remove 62% of that resistance, the human body immediately interprets it as a signal that it is overbuilt for its environment. It begins to systematically dismantle its own structural integrity. The most immediate casualty is the skeletal system. On Earth, our bones are dynamic tissues that constantly rebuild themselves in response to the mechanical stress of supporting our weight. In the low gravity of Mars, that stress disappears. The body stops investing energy in maintaining bone density, actively dissolving the calcium matrix of the skeleton and flushing it out through the urinary tract. Astronauts in microgravity lose up to 1% of their bone mass every single month. While we don't yet know the precise rate of bone loss in Mars's 38% gravity, it is certain that over a multi-year deployment, colonists will suffer from profound, irreversible osteoporosis. Their bones will become brittle, porous glass. If they ever attempt to return to Earth after a decade on Mars, the sudden re-entry into a one-gravity environment would literally shatter their legs and collapse their spines. The muscular system follows the same trajectory of decay. Without the need to fight against Earth's heavy gravity to walk, sit, or lift, the body's skeletal muscles rapidly atrophy. But the most dangerous muscle loss occurs in an organ you cannot see, your heart. The human heart is an incredibly powerful pump designed to push blood upward against gravity from your feet back to your brain. In the low gravity of Mars, the heart doesn't have to work nearly as hard to circulate fluids. As a consequence, the heart muscle begins to shrink and remodel itself, losing its mass and structural capacity. The blood vessels themselves lose their elasticity and their ability to regulate blood pressure effectively. Over time, the colonists' cardiovascular systems will degrade to match the low demands of Mars. They will become permanent prisoners of the red planet's weak gravity, biologically altered into a state where returning to the heavy gravity of their home world would cause immediate cardiovascular collapse, profound fainting spells, and systemic heart failure. Act 16. The neurological blindness. The systemic decay triggered by low gravity is not limited to bones and muscles. It reaches deep into the delicate fluid mechanics of the human skull, threatening the very sense we rely on most to navigate the world, our vision. This is a medical phenomenon discovered only recently through long-duration missions on the International Space Station, known as Spaceflight-Associated Neuroocular Syndrome, or SANS. On Earth, gravity pulls the fluids in our bodies downward, maintaining a healthy balance of pressure between the head and the torso. In a reduced gravity environment, this downward pull is drastically weakened. Fluids, blood, lymph, and cerebrospinal fluid shift upward, migrating into the head and chest. This fluid shift causes a permanent, unnatural elevation of pressure inside the human cranium. This persistent internal pressure begins to press against the back of the eyes. It literally flattens the shape of the eyeball over time, distorting the lens and forcing the optic nerve to swell and inflame. Astronauts who enter space with perfect 20/20 vision return to Earth with profound, permanent visual impairment, suffering from severe hyperopic shifts, blind spots, and choroidal folds that cannot be corrected by simple glasses. On Mars, this fluid shift will be a permanent, daily condition of life. Over years of living in 38% gravity, the colonists' eyes will slowly deform under the relentless pressure of their own shifted cranial fluids. They will be forced to operate advanced machinery, perform delicate maintenance tasks, and manage hazardous airlock procedures while their vision is systematically clouding, blurring, and failing. And the pressure doesn't just attack the eyes, it alters the fundamental mechanics of the brain's waste clearance system. During sleep, the brain utilizes cerebrospinal fluid to flush out metabolic toxins and cellular debris that accumulate during waking hours. This process depends on precise pressure differentials. With the constant upward fluid shift of a low-gravity world, this drainage system becomes congested. The long-term cognitive impacts of a permanently congested, hyperpressurized brain are deeply alarming. Colonists may face accelerated cognitive decline, persistent headaches, sleep disturbances, and an inability to maintain the intense concentration required to survive in an environment where a single mental mistake can cause a habitat-wide disaster. The body is not a collection of modular parts you can swap between worlds. It is a highly integrated, finely tuned machine designed for Earth, and when you alter the gravitational input, the entire system begins to drift toward neurological and physiological chaos. Act 17, the illusion of multi-generational continuity. When we read the grand manifestos of space colonization advocates, the narrative always extends far past the initial scientific outposts. They speak of Mars not as a research station, but as a new cradle for human civilization, a place where families will be raised, children will be born, and generations will grow up calling the red sands home. This is the ultimate benchmark of a true colony, the ability to self-replicate without a continuous injection of human capital from the mother world. But this entire multi-generational vision is blocked by an absolute biological blank space. We have absolutely no data on whether a human embryo can develop normally, or if a mammal can successfully gestate within a 38% gravitational field. Every single instance of human reproduction in our species history has occurred at the bottom of Earth's one-gravity well. Embryonic development is a masterclass in microscopic physics and fluid dynamics. From the moment of fertilization, the division of cells, the migration of tissues, and the structural patterning of organs rely on subtle mechanical cues. The developing embryo uses the constant downward pull of Earth's gravity as a positional guide to determine up from down, left from right, and front from back. It is the invisible scaffold upon which the entire architecture of the human body is built. If you remove nearly 2/3 of that gravitational scaffold, the biological blueprint is thrown into complete disarray. Preliminary animal studies conducted in microgravity on orbital missions paint a horrifying picture. Fruit flies, fish, and mice, gestated in zero gravity, exhibit severe, lethal developmental deformities. Their skeletal structures fail to fuse, their internal organs form in the wrong positions, and their central nervous systems develop into scrambled, non-functional networks. While Mars does have some gravity, we do not know if 38% is enough to clear the critical threshold required for normal human gestation. If it is not, then a Mars colony can never be a civilization. Any pregnancy attempted on the red planet could result in a tragic cascade of spontaneous miscarriages, stillbirths, and severe life-threatening congenital abnormalities. Imagine the psychological and ethical horror of a community where the first children born are systematically deformed, their bodies unable to support life, because the planet itself refused to provide the gravitational framework their DNA expected. To find out if human reproduction is even possible on Mars, we would have to treat human women and their unborn children as experimental subjects in an unshielded, low-gravity, high-radiation laboratory. It is an ethical boundary that borders on the monstrous, and if reproduction fails, the colony ceases to be a living community. It becomes nothing more than an expensive, multi-trillion-dollar terrestrial nursing home on a distant rock, entirely dependent on a continuous stream of new immigrants from Earth who are willing to sacrifice their health and their reproductive futures to keep a dead dream alive. Act 18, the tyranny of the logistic lifeline. To truly understand the isolation of a Martian outpost, you have to look at the geometry of its orbital relationship with Earth. The two planets do not sit stationary next to one another. They are two runners on concentric tracks, moving at different speeds around the Sun. Earth completes its circuit in 365 days. Mars takes 687. Because of these mismatched orbits, the distance between our home world and the red planet is in a state of constant, dramatic flux. Once every 26 months, the two planets align in a configuration called opposition, coming relatively close to one another, though close, in astronomical terms, still means roughly 34 to 60 million miles away. This brief alignment opens up a narrow, highly critical launch window. If you miss this window, the door slams shut, and you must wait more than 2 full years before you can attempt to launch another payload to Mars. This orbital synchrony imposes a brutal, unforgiving rhythm on the logistics of survival. A trip to Mars using our most advanced chemical rocket propulsion systems is not a quick voyage. It is an 8-month crossing through a deep space radiation environment. This means that if a critical component fails inside the colony's life support system, if the primary seals on the water recycling unit degrade, or if the main computer core governing the nuclear reactors suffers a catastrophic short circuit, you cannot call for a replacement part. There is no emergency overnight shipping to Mars. The colony must possess an exhaustive, infinitely redundant inventory of every single screw, valve, chip, and gasket that makes up its sprawling industrial infrastructure. If they run out of a single, specialized component, and their 3D printing systems cannot replicate it due to a lack of raw precursor materials, they must wait up to 2.5 years for the next cargo transit to arrive. This logistical gap becomes terrifying when you consider the scale of mass required to sustain human life. Every individual on Mars consumes roughly 1 metric ton of dry food, oxygen buffer gases, water replacement reserves, and medical supplies every single year. For a colony of 100 people, that means 100 metric tons of raw survival consumables must be successfully launched from Earth, survive an 8-month transit through the void, endure the violent, terrifying process of atmospheric entry and landing on Mars, and be delivered undamaged to the habitat gates between every single orbital window. The economic and structural cost of maintaining this lifeline is staggering. It requires a continuous fleet of heavy-lift rockets launching from Earth at a scale that would dwarf the entire global aerospace budget. If an economic collapse, a global war, or a systemic industrial crisis should strike Earth, and the launch manifests are interrupted for even a single window, the lifeline is broken. The colony on Mars will watch their supply reserves slowly tick down to zero, completely helpless, knowing that no help is coming across the void. They will be left to suffocate or freeze in the dark, a handful of forgotten ghosts on a world that never wanted them there in the first place. Act 19. The Economics of Total Dependency. The absolute lack of a self-sustaining economy on Mars is the quiet financial anchor that drags the entire concept of colonization down into the realm of impossibility. For an outpost to truly become a colony, it must eventually generate something of value, an export, a resource, or an industrial product that it can trade with the outside world to pay for its own upkeep and importation needs. On Earth, historical colonies were driven by powerful economic engines. The Spanish, British, and Dutch outposts in the New World were brutal, dangerous undertakings, but they were fueled by the extraction of tangible, high-value wealth: gold, silver, timber, tobacco, sugar, and spices. These resources flowed back to the mother countries, generating immense profits that easily justified the staggering cost of building and maintaining the shipping fleets that kept the outposts alive. Mars has no export economy. There is absolutely nothing on the Martian surface that can be mined, processed, and shipped back across 142 million miles to Earth at a profit. Let us assume Mars is rich in rare earth elements, platinum, or diamonds. The cost of launching a rocket off the surface of Mars, accelerating it through deep space, decelerating it into Earth's orbit, and landing it safely is so astronomical that even a payload of pure, solid platinum would be worth a fraction of the fuel and engineering costs required to transport it. It is a thermodynamic and economic absurdity. The only asset Mars can theoretically produce is information, scientific data, intellectual property, and research findings. But you cannot feed a population on intellectual property. You cannot build airlock seals out of scientific papers. The colony will remain entirely, 100% dependent on massive, unceasing subsidies from the governments or corporations of Earth. It will be a permanent financial black hole, consuming hundreds of billions of dollars every year with absolutely zero financial return on investment. In the cold world of global economics, permanent subsidies are the first things to be cut when times get tough. The moment Earth faces its next great systemic crisis, whether it is a major economic depression, a catastrophic climate shift, or a resource war, the multi-billion-dollar annual check to the Mars colony will be viewed as an unconscionable luxury. The funding will dry up, the launch schedules will be canceled, and the colony will be left stranded. Mars does not offer an economic frontier. It offers an expensive, high-maintenance museum that can only exist as long as the world it left behind remains wealthy, stable, and indulgent enough to pay its bills.